Alright, welcome everyone, FreakMod here. Pretty much what we're going to be doing today is a completely blind solve of level 14 teaching 1, which is the first Yan85 challenge. I say blind because I'm going to do it basically start to finish, and I don't remember too much about the challenge at this point. So the essential goal is show you how I approached it, kind of walk through it, and find the solution after a while. So first thing we can do pretty much religiously is run the challenge, see what happens. Let's minimize you. So as you can see, we have a lot of output, and it's telling us that we have a custom emulator, it's completely custom architecture, that's Yan85, and then it spits us out a whole bunch of erroneous information. Now, personally, I like to sort of categorize whenever I get like interesting output from one of these programs. So we're going to copy all this, dump it into a text editor. Oops. Yeah, do that. Let's give Adam a second here to decide that it wants to start. And let's paste this in here. So from what we can see right away, we notice that there's basically like a repeating pattern here of like this V, I, and S over here on the other side. I'm personally a very pattern-driven person, so I'll always look for that when I can. And it seems like we're printing out what appear to be like variables. It appears we have some sort of raw instruction, and then some sort of maybe like S, maybe like semantic instruction or string representation, however you want to call it. And at this point, like, you can look at this for a while, but generally I don't like to puzzle over the output for like an extremely long time, so instead I'll just like jump straight into a disassembly program. My program of choice here is Ghidra, and so let's see. Pretty sure I downloaded this binary a second ago. Yep. So let's pull this out, dump this in here. And so Ghidra's pretty good, highly recommend it. I don't like Binary Ninja as much just because it's in your browser and that's annoying to me. And so essentially when you open something up in Ghidra, it'll yell at you if you want to decompile it or not, or perform like analysis as they call it. The way you can do this manually is up here. You have this analysis tab and you can auto-analyze a program. And you don't have to worry about any of the options, anything like that. Just smack the analyze button. And over here in your symbol tree, you can expand it and find a whole bunch of different functions. So generally our starting point is always going to be main. And we can just kind of begin looking through this. And so one interesting thing that we see right away is that we're printing out our stuff, and then we're doing a whole bunch of weird back-end crap that we don't really care about, at least not yet. We have a memcopy instruction down here, which is interesting to me. And then we're also calling this other function, which is called the interpreter loop. And so if we take a look in this interpret folder over here, we'll find that interpreter loop function. And so as you can see, what we're passing into this function is this local 418 variable, which, as you can see, is actually given to us from memcopy. And knowing how memcopy works in this instance is pretty helpful. For example, we have a destination, a source, and then a size n. If you mouse over, it'll tell you this information. Essentially what this means is we are copying n bytes from the source to the destination, and double-clicking on any one of these will bring you to like where they're defined. So if we want to find out what we're copying, we can double-click on VM code, and it's going to give us a whole bunch of raw bytes. And this looks interesting to me, so I'm going to copy this out. And this might take a second, depending on how long this is. Oh, I went way too far. And then there's the end of it. So let's copy that. Let's dump that into a text editor as well. And so it says like undefined because it doesn't know how to interpret like 1 byte most of the time. So let's perform a column select and pull out all of these raw bytes. And essentially what we're doing is we're trying to isolate this data because we don't know what it is yet, but we know it's probably relevant, so it's being passed into the functions that are being called. I hate this operation, by the way. If anyone knows a faster way of just like jumping to the top of your file, let me know. So it looks like O2 is our first one here. So let's cut all these out, dump them here. And we could clean this up even more if we wanted to. Like, for example, we could replace new line characters with just like a space or something. Just like that. And so here's our raw sort of bytes that are being copied into that buffer. And with that down, let's keep examining what's going on. So if we double click on our interpreter loop here, it'll pull us into this function. And as you can see, it says that we're starting the interpreter loop. Now, at this point, generally when there's print statements, I'll be comparing it to the output. So like as you can see, we do have that print statement here. So that means we actually hit this in our execution. Sometimes you'll be analyzing functions and you'll see a print statement that it doesn't actually show up in your output. That's always something interesting to watch out for. It's like a little litmus test. So then we just have a while true loop. And I always like to pull these loops out, or just like bits of code that I think are important. And I'm just going to pull them into a notepad and just kind of start getting rid of some of this junk in here. Because as you can see, there's a lot of like pointers and casts all over the place that can sort of be reduced, because we're not going for like strictly compiled code. We're going for a general idea of how the program works. Now, we already know that param1 passed into this program was the offset at which our Yan code was read into memory. So we can essentially treat param1 as some sort of offset that's like a mystery. We don't really know what it is yet, but we know that it's an offset. We know that it could be relevant in the future. Let's double check our recording, still going. So let's continue looking at this. So we have bvar1 is equal to a byte. It's being dereferenced. And essentially we can reduce it to this. We can also reduce that to that. Equals bvar plus 1. So literally what this is this right here is an incrementation, because we're loading the value at this offset plus OX401, and then we're storing that exact value plus 1 back in that exact location. So essentially, we can say plus equals 1. Now, I like using Python formatting to do this, so I'll be like, while true. And then here we have a uvar2 is equal to a whole bunch of extra junk, which is bvar times 3 plus param1, which to me looks a lot like an offset, but who knows? We don't actually know yet. And if we paid attention, bvar1 is actually that offset that we just implemented, so we could say that, come on. I hate when these don't line up anyway. bvar1 equals this. So it looks like we're grabbing something and then adding some sort of offset again, and then we're passing into this interpret instruction function. Now, this is still a little bit cryptic, but we're going to continue finding out what it is. Like, we don't need to know, we don't need to understand everything through our first pass. So let me head into our interpret instruction function. Instantly right here we see a really handy printf statement, which is that v like prefix statement that we saw earlier, which is all these variables printed out. This means that we can actually find out these variables are stored. And if we look, it's that similar formula that we just saw earlier, which is this param1, which we know is the base pointer to where our memory was stored, and then we're adding some set offset to it. And so in this case, we can copy this out, because this is relevant information, and we can kind of decipher it. And we can essentially say that in this case, well, we have A, B, C, D, S, I, and F. And note that at no point am I like trying to like jump too many steps into the future. Like, I'm just taking this slowly. Like, we're trying to peel back one layer at the time rather than like digest like the entire elephant of information at once. And that really helps. And note that printf statement is just going in order. So at this point, we now know exactly where every single one of these variables lives based off of this. Because as you can see in our printout, we're actually printing those values. So that's very useful. And I'm just going to call these registers. So as we continue, we see some more useful information, and then we're printing out something interesting here as well. So let's dump this in here. So as we can see, we're taking this param2, which we're unsure of what this is right now. If we go look at our interpreter loop, param2 is this guy right here. And so not entirely sure what that is yet, but that's okay. And so we can very quickly see that param2 is being compared to a whole bunch of values down here. And based on that, we're calling different interpretation functions for operations. This suggests that param2 is probably some kind of opcode. And if we look at this printf statement, op, arg1, arg2, and we see local 18, cstack22, and cstack23, well, that's really easy to interpret. It means that param2 is our opcode. It means that this cstack22 in this case is going to be arg1, and that this cstack23 is going to be arg2. Now, what does this actually mean? Well, this is taking parameter 2 and shifting it, bit shift, over by either 8 bytes or 16 bytes, or not bytes, bits, sorry. So when you shift something over by 8 bits, you move to that next byte over. And so we can actually take a look at our output and see that we have an op of 2, an arg of 1, and an arg2 of 27. And if we look at our very first set, our very first like kind of triplet here of bytes, we see that 022701. These are the same values, but you'll notice that the third value in happens to be arg1. This means that our, I guess, like ordering is not consistent. It's not opcode arg1, arg2 every single time. Or, well, this will remain consistent through the entire program, but it's not like given to you for free, essentially. So this means that our ordering, in this case, is going to be opcode arg2 and then arg1. And like this might seem kind of backwards, but like it changes later. So like you have to be careful. It's one thing you just had to like find, I guess. And then at this point, we can start comparing our opcode with numbers. And we see that based off this, we're calling a whole bunch of different functions. So in this case, we can say that we can make like a little table of our opcodes. Now, here we see that if we AND it with 2, we get an immediate. So im is going to be OXO2. When we AND it with 40, we get add. When we AND it with 8, we get STK. And like, I don't know what these instructions do yet. I'm just writing it down. And then 1, we get STM. Come on. And then for 20, we get, what was that, LDM? Yeah. And all I'm doing is I'm looking at this value right here, and then what it's calling. So for comparison, or CMP, we're getting 10. And then for jump, we get OX04. And finally, we have this syscall, which is like this weird less than a null byte. At least that's what I would guess this is right here. Not entirely sure. And so we could say that sys in this case just OX00 or 0. And then I'll generally sort these out because I have some OCD. Makes me happy. And so the entire question now is just like, what does each one of these do? And well, we're going to get there. So at this point, we can start investigating these interpretation functions and figure out exactly what's going off. Or I guess going on. So in this case, it looks like we're writing to a register. And so it looks like we pass in our offset. It looks like our offset is being passed around the program, so that's just something to keep in mind. Oops. Never seen that one before. And so then we're passing in bstack38, bstack39, and it looks like bstack38 again, but this might be a bug. Sometimes Ghidra likes to add in extra function arguments when you leave it in one of the argument registers on accident, or well, not when you leave it, but when the bytecode does. So just something. Don't read too much into what Ghidra spits out as a decompilation. You should take it with a grain of salt, honestly. So let's look at this write register function. And so as you can see, we have 3 parameters, and it looks like we are writing, and we know that all of these are variables already, or registers. Like these are the registers here. We have the param1 plus the offset, and being set equal to parameter 3. And it looks like, based on what parameter 2 is, it's giving us a different one of these registers. So this is a pretty good suggestion here, that our registers have some sort of internal coding. So registers in this case, we can say this case 1, which is OXO1, is going to be 3FF, which is D. So I guess we could put this up here, or OXO1. And let's continue looking. At 2, we have 3FC, which we can see is A, so or OXO2. For 4 right here, we have 400, which is or OXO4. So that's S. At 8, we have 3FE, which is C. At 10, we have 401. And then at 20, we have 3FD. And then finally at 40 down here, we have OX42. And so, like, interesting stuff going on here. And knowing this, we can kind of verify too. Like, we saw that our first instruction was an immediate D, and the arg1 was OXO1. So that means that OXO1 should correspond to D, and we do see that that is the case. So that's just some indication that we're moving in the right direction. So now let's continue interpreting our instructions. So we can make a little comment here next to immediate. Loads arg1 into register arg1. Then let's take a look at add, which looks to write the value of register 1 plus register 2 into that other register, because we already know how this write register function works. So you can say adds values in registers arg1, arg2, stores in arg1. All right, let's continue. Let's see, our next one, I guess we can, I'll go back to this entire, so our next one is stack, or STK. So now the key hint here is you see a push and a pop. And so what it looks like is that this is going to go ahead and be pushing whatever is in arg1 and popping whatever is in arg2, or well, popping into arg2. So stack pushes in immediate in arg1, pops into register arg2. Now, there's a couple interesting things we can actually glean from this. We can also see that every time we perform a push or a pop, we're modifying this variable at OX400 by 1 or -1. So that means whenever we push, it's increasing, and whenever it's popped, it's decreasing. This sounds a lot like a stack pointer, and it happens to be dealing with this register F, or S. So we can see that this is our stack pointer. This essentially is the length of our stack. And we can see that it's actually being used. So that is pretty interesting. So nothing else really to go over here. Let's head back, STM. So let's see what STM does. So we're describing 2 registers, describe registers, grabbing those values so they can print them out. And then it looks like it's reading these 2 registers. And then it looks like it's writing the memory from the first register to the second register. So if we take a look at this write memory function, yes, all it is doing is offsetting by the second parameter and setting it equal to parameter 3. So this could simply be interpreted as, I guess, arg2 pointer equals or sorry, arg1 pointer. Whatever is pointed to by arg1 is set to arg2. And that's in our memory. So that means, like, as an example, like, and it looks like these are actually registers too. Like if we went back and like actually looked. Yeah, so they're reading the registers. So it points to register arg1 and it sets it equal to the register in arg2. Let us continue. So LDM. I'm assuming this is the exact opposite of SDM, but we're going to double check anyway. See, as you can see right here, load dedicated memory, and it's going to pull into this value that what is pointed to by arg2. So loads value pointed to by arg2 into arg1, or I guess register arg1. And then let's go to CMP. So as you can see, there's some interesting things going on here. So comparison generally, if you know how the x86 variant of it works, it will compare the values and then based on the output, it's going to set some flag register. And if you'll notice, we're actually performing comparisons on both these arguments. And then we're modifying this register 402, which is F. So this is our flag register. And based on the output, we can make some sort of little reference down here. If arg1 less than arg2, flags are ORed with 2. LF arg2, or I guess arg1 is greater than arg2, that's what that would parse out to. Flags is ORed with 4. LF, and these aren't LFs, my bad. These can all happen at the same time. Like, these two can't, but the rest of them can. If arg1 equals arg2, flags is ORed with 8. And then if, I guess we would have an else down here. So else would be if arg1 is not equal to arg2, flags is ORed with OX10. So that's 16. And if arg1 equals 0 and arg2 equals 0, then flags can be ORed with 1. All right. So we took away some pretty interesting information from that. This is just something to keep in mind in the future. So I think the only instruction we have left is jump. Described below. And then also sys. So let's take a look at jump first. As you can see, it's checking some condition here, and then either taking the jump or not taking the jump. And it looks like the comparison is pretty interesting because it's based off of the flags, which is in bstack38, and it's ANDing this value with them. This means that the flags probably have some pretty decent relevance here. So if we take a look at our jump flags, which traditionally they work pretty similarly, we can see that we have a couple different values here. We have 4, I guess, OX04, OX08, OX10, OX01, OX00. So let's go ahead and then, oh, we also have a 2 up there. And it looks like each of these sets the value equal to the ASCII value and then increments it by 1, meaning this is assembling some sort of string. And that's especially evidenced by the fact that we're ending it with a null byte. So let's pull up a UTF-8 table. So if we take a look at our UTF-8 table, we have, I'm going to put this down here, put you up here. So OX00 is OX5A, which if we look at our table, that's going to be equal to a Z. So string plus equals Z. OX01, we have 5A. Oh, wait. We have, oh, so this is 2A. my bad. That is an asterisk, and that means this one is a z. So that means an asterisk is probably an unconditional jump. So for O2, we have 4c, which is a capital L. What? What is that there? Oh, disgusting. Then we have O4, which is OX47, which is a capital G. We have an O8, which is 45, which is a capital E. And then we have our OX10, which is 4E, which is an N. And so these are probably combined in some way. And we can kind of look for that evidence if we look at our program output, maybe look up a jump instruction. So yeah, here's a jump with an N flag, here's one with an E, and here's one with an LG. Oops. So you can see right here. So kind of interesting. I need to sneeze, hold on. Okay, we're back. Sorry about that. And so let's continue. Now we just need to do sys, which is our last one. So as you can see, right away it looks like we're ANDing the parameter 2, which is our offset with these pretty large values, but note that these trailing zeros don't actually do anything here. So we have OX08, I think, yeah, and then OX01, OX404, OX02. That's an OX20, OX10. Note that I'm just looking at each of these if statements and looking at the value after them. And it looks like we don't have an OO option. So yeah, we have 1, 2, 4, 8, 10, and 20. That does line up. And so it looks like our O8 is going to be an open syscall. And it looks like our O1 is going to be a read syscall. O4 is going to be another read. O2 is going to be a write. 2O is going to be a sleep. And then 1O is going to be an exit. And as you can see in each of these syscalls, we have registers here. So let's make a quick mock-up of what's going on here. So 3FC in this case is A, so we're exiting with A. We are also sleeping with A, as you can see over here. We are writing param1, write with, that is A, and then an offset of 3FD, which is B. So write A and B. And I'm assuming what's also probably, let's look at the write syscall. I don't remember that off the top of my head. Let's take a look at the man page for this. So write takes in file descriptor and a buffer, and then our count is this n bytes 00, which I'm assuming is probably some constant that's stored in the program somewhere. Or no, it's actually right here, which is OXFF minus 3FD. So it's going to be C here. So that makes me think that these are just in order, which does make it kind of convenient for us. So once again, that's going to be A, B, and C for our read calls. There's probably some semantic difference in here, but it's not too important for me right now. I mean, if we need to come in and dissect this even further, we very easily can. And then finally, our open is 3FC, 3FD, 3FE. Yep. Also A, B, and C. All right. So at this point, we've kind of created kind of like a textual, I guess, like dictionary for what Yan85 is doing. But the real question is how does that help us solve this problem? And well, the solution that I gravitate towards always is to try and figure out exactly what the program's doing at every step. And so what I want to be able to do is know how this translates to this. And so my next logical step was to write essentially a disassembler to take this and convert it into English. Now, we're a little bit interested in some things here. We still have some missing gaps. And one gap that we have is we have this I register that's kind of a mystery right now. But if you remember that while true loop at the beginning, you'll notice that it's incrementing 401 every single time. That makes me think that this is an instruction pointer. And granted, that could change in the future. But once again, it's always nice to have like an initial set of observations and then slowly work with them over time. I guess that's unnecessary now. So let's go ahead and begin writing in disassembler. So let's save this, I guess is like, overwrite my existing one. And let's begin to think about how we might write this. One thing that will initially help is probably saving this. I guess I'll overwrite my old one as well. And generally, like what we need to do first is figure out how to read this into our Python script, because I'm going to be using Python for this, as you can see by this .py extension. So let's see, input file. And let's see, this is input the text. We need to open this as for reading. Let's grab all our lines out of the file, which is just one. And then we can print these lines out. And let's grab a console to go ahead and help us test this. So as you can see, we have all our data in here. That's nice. So then we can grab our code, I guess. So let's take that first line, strip all the crap out of it, and then split it by the spaces that we put in here. You could put commas there pretty easily, I guess, if you wanted to do that. So now we have all our bytes split up and in a nice giant list for us. And what we need to do is we know that these are combined into triplets of 3. It's an opcode, then an arg2, then an arg1. So we can use some nice little list construction to do that. Let's see, it would be I plus 3. So we need to strip out 3 every time for I in the range of 0 from the length of all the code. And then 3. And then we should, at this point, be able to say for instruction in Y code, print instruction. And that should give us these tuples. Oh, oops. Oh, I put an S there. All right. And then now we have all our instruction sets. So since we know that we have an instruction pointer that's incrementing every time, it's probably smart to label each of our instructions with that hex offset. So we can print that hex out. I guess put some fancy formatting in. Do that, and then I guess we can also print this after that. Let's test how it works. Oh, we got to increment it. There we go. And now we have all our offsets. Cool. And now we just need to convert this into English, which probably isn't that hard. Well, I hope it's not that hard. So let's see. Our opcode in this case is going to be the int at instruction O, and it's going to be base 16. Note that these are hex values, so you might as well convert them straight to base 16 integers. Excuse me. We know our arg2 came next. So that is going to be instruction at 1, base 16, and then finally our last one right there. So now what we should be able to do is print op arg2 arg1. Get rid of that. Oh, I got rid of an extra parenthesis. I got rid of way too much. Fix all my spelling mistakes. Actually, let's just make that lowercase. That'll make my life easier. There we go. And now we've got all those values. And let's begin converting. So we can say if op equals, and let's start with OXO actually. OXO in this case is going to be print sys elif op equals OXO1. We have print stm elif I, these are all lowercase. I'm going insane. OXO2 print immediate elif op equals OXO4. We have a jump elif op equals OXO8. We have a print stack. And if this bores you, you can probably skip ahead in this video. I'm just doing this for like, I guess like the sake of doing it. So CMP, let's add. And then let's get rid of this. Test this out. Oh, we should probably have an else here. Just to see if we messed anything up. I'm missing a double equals somewhere. Alright, so we do some errors. Let's double check what those are in a second. Everything else seems to be accounted for. Looks like the instruction at 33 is erroring out. Let's print that opcode just to see what's happening. Looks like that's the opcode of 128, which is OX80. So that might make me think at some point that... Interesting. This makes me think that since the last line is all zeros, we know that because we saw that earlier, right? Yeah, so we have 3 zeros at the end. This makes me think that OX080 is probably sys instead of 0. Yeah, in this case, only our last line, which is the 0. So that's fine. We'll just say else continue, which we probably don't even need, honestly. So at this point, we just need to figure out the rest of this junk. And in order to do that, we need to probably write some extra functions. Because let's start with an easy one, which is immediate, right? Immediate prints out 2 other registers, so we need to resolve these registers. Resolve. What? Did I type that? And then let's define this function. Let's just take in some input. And then I guess probably just like an if statement is probably the way to do it. I guess we don't need to copy. So let's see. Let's see. 2 is going to be A. Don't need else here because we're returning. 4 is S. 8 is C. 10 is I. 20 is B. And then finally, I think we have 40, which is F. 1, 2, 3, 4, 5, 6, 7. So that should work fine. And then let's double check where we needed these registers to be resolved. So sys has, take a look at our output and just look for sys. So sys has a code and then a register. So we can make some resolve sys call here for arg1, and then resolve register arg2, stm, which is looks like a pointer c equals d. So let's see, pointer, I guess we should do this. And that, there should be an equals in there actually. And like we'll fix this as we go. I'm not expecting it to be correct on the first time around. Let's see, jump, no, in this file, man. Looks like jump and then our flags. Okay, so we'll have to resolve our flags. We have STK, which is just 2 registers once again. We have compare, which also should be 2 registers. We have LDM, which should be similar to set memory. So 2 more resolve registers. Let's fix that. Let's look for an LDM call in here. We have then a register equals star plus that. And then finally add is once again 2 registers. So that's fine. So we have resolve flags, which you can skip, and resolve sys, which we can also skip. Oh, immediate shouldn't have a register on it. That should just be R2, pretty sure. Yeah, if we look for immediate in here, yeah, R2 is a value. So let's double check this. Expect an indentation block somewhere. Oh, I gotta do pass. Then an unmatched somewhere right here. Alright. So it looks like everything's looking pretty good. Stack has none, so that's not good. We're seeing we're loading a lot of things in. Okay, so we'll uncover those in a second. Let's continue resolving our sys calls. Or let's do our flags first. So we can say def resolve. So we can say flags just some empty string. If input and OXOO FL plus equals a star. If input and I guess this should be equals 0. OXO1 equals 0 plus equals a Z. At this point, you can start copying and pasting. And you turn out the autocomplete. Sometime, not now. L. We have OXO4 is G. And we have O8 is E. And then we have 1O, which is, and this should be a does not equal 0. If I'm remembering this properly. Then we should be able to return FL. So now that's our flags resolved. Now we just need to resolve our sys calls, which should be very similar to resolving a register. Oh, no wonder. Duh. Why did I write arg1 here? We're big braining. That's why none of our registers are resolving. Alright. So O1 syscall is read. And I guess we can put the read ABC here. O2 is write. O4 is another read. There's some sort of difference between these two. If we actually go back and look really quick. This is read code and this is read memories. Let's make that distinction. And then on O8, we have open. 10, we have exit. And then on 20, we have sleep. All right, let's test. I guess I should clear this. And now we're talking. All right, now pushing a whole bunch of things onto the stack. All right, yeah, looking pretty good. So now that we have this, we actually have our raw Yan code. Like, it's decompiled. Like, this is exactly what it's doing. And now it's kind of up to us to figure out exactly what's going on with this. So let's take this output. And we have a dead value at the end there, just because it's that 0, 0, 0 that I was talking about earlier. And now we can just begin executing this, really. All right, welcome back from an abrupt cut. Might have forgotten to do some homework that was due for another class, but we're back in it. So we wrote our disassembler, and now we have our output of exactly what the Yan code is doing at every step. Like, this is our raw source code. And once you get here, there's a number of different approaches that you can actually take. The best, like, the way that I did it was I did it by hand, personally. You don't have to do it by hand. You could very easily write an emulator for this architecture. I just didn't really want to worry about it that much, honestly, so I just did it by hand. So that is exactly what we're going to do. So now, in order to set it up by hand, we need to go ahead and just like kind of like set up some basic things. Personally, the first time I did this around, I did it in like an Excel spreadsheet. Today, we're just going to notepad it, and we're just going to drop in all our registers, drop in a stack, drop in some memory, and then we can go ahead and get started. Also going to go ahead and reconnect to the server. Come on. Just so we can have that output one more time. So we're going to go ahead and grab this, just because it might come helpful later. So, oops. All right, so now what we can do is we can go ahead and begin to evaluate this code by hand. And pretty much we know our entry point, because if we scroll up to the very top here, we see the first instruction executed is OX1. So we know we're starting at the top and just working our way down. So there's easy way and hard ways to do this by hand. Personally, I took a lot of shortcuts while doing it because my goal was to understand the code, not to just execute it line by line and then potentially get stuck. And so what I did was I just kind of took like a quick look over this code. Like, you'll notice that we have like a couple of syscalls here. It's like we have a write, we have a read, and then we have another write, we have an exit, we have another write, we have an open, a read, and a write, and then an exit. And so what I did was I kind of looked above each of these write syscalls, because these write syscalls have to write something that is, I guess, relevant out. And when I was looking above this, I noticed that this was loading a lot of information onto the stack, and I wanted to know what that information was. So what we can do is look at converting hex to UTF-8. Hold on. And by doing this, what we can do is we can see what's going on here. So for example, we push OX49 onto the stack. Then we push OX4E onto the stack. Remember that the stack instruction is going to pop into the left and push the right. Then we're pushing OX43, OX4F, OX52, OX52, OX45, etc. And by doing this, we can say that this write call right here, this is printing out incorrect. And so we can make a mental note that we want to avoid ever executing OX71 plus. And the reason for this is once we execute this OX71 line, you'll notice that there's no way to actually escape this write call, followed immediately by an exit. And so we definitely don't want to do that. Then we see another write call followed by a whole bunch more stack, I guess, like stuff. OX4F, OX52, OX52, OX45, OX43, OX54, OX21, and just those right away, we see that it's printing correct. And so then it's probably loading like, here's the flag or some other variant of that message in, and then it's writing it. Then it's performing another set of set memories. It's opening a file, reading, and then writing. Now, I'm assuming that these values right here are going to go point to the flag. So if we start at OX2F, OX66, OX6C, and as you can see, we're getting that flag string starting to appear down here. And so this means that our goal is to execute this OX8E instruction. So we want to avoid completely OX8D or OX71 to OX8D. We want to hit OX8E. Now, because there's an exit call right here, it makes sense that at some point in the program, you must have to jump to this address somehow. And so we can do a quick little search, or sorry, it would be for the one right above it. So OXD. And as you can see, this value is loaded into the program at some point. And then directly afterwards, we see a jump. And so we can continue kind of working backwards. So we want to hit OX8E. So this means we want to jump to OX8D. This jump occurs on line OX6E. And it is a jump equals. So this means that D and C must be equal on line 6C. And as we can see, C is loading up a 0 value. And so this means that C must be equal to, or D must be equal to 0. And we can continue kind of looking backwards a little bit. So we're pushing D onto the stack. And it's actually kind of interesting here because this line right above 6B is an immediate jump. So this means at some point we also have to jump to 6A. So let's take a look for that. Interesting. Sometimes the value can like be created mathematically and then pushed onto the stack or jumped to like that. But you'll notice that this is jumping straight away from it. So at some point in the program, we'll probably jump over to 6A or 6B. So now that we kind of know what we want to do, now like we have like our target. Like we want to jump to OX8D. And we need to pass this check at OX6C. We can start sort of working our way through the program and seeing exactly what's happening. So at this point, I would begin executing because we hit a dead end when working backwards. So the first thing we're doing is we're loading some values in. Let's initialize all our registers to 0 except for 1, or except for I, which should be 1. It's also important to note that our stack and memory are currently empty, or should be uninitialized. And I'm not going to go through and execute every single one of these lines by hand, line by line. There's faster ways to do it. For example, you can look at these 3 instructions right here. You'll notice you're loading a value into D and C, and then you're setting the memory pointed to by C equal to the value of D. So this means those 3 instructions is simply saying at OX9C, we have OX27. Then we repeat that process again. So at OXAO, we have OX97. And then at OX9D, we have OXB9, OXA5, OXBO. I don't know if OX is the right way to say that, by the way. It just makes sense to me. I guess I'll drop it, but... So then we have A1, which is pointing to 5D. And then we have 9B, which is pointing to E2. And then 9F, which is pointing to C9. Really quickly, I'm just going to sort these values. It makes things a little bit easier when you know that they're in order. just because we don't know at some point if there could be like a sequential read. And so it's kind of important to keep things in check. So let's see, this one would go right here. It would go right here. All right. Yeah, BCDF 015 makes sense. So at this point, we know that the values in D and C is 9F in C and C9 in D. And then we also know I at this point is going to be equal to 16 because that's the instruction we're executing. So we just kind of like ran straight through these first set of instructions. At this point, we're pushing A, then we're pushing B, and then we're pushing C. So this means we're pushing two 0 values, and then we're pushing OX9F. Now, remember that we already know from our disassembly that whenever you push something onto the stack, it's going to increase this stack pointer, which is stored in S. So that's going to be 3. Then 19 says load 1 into B. 1A says add B to S, or add S to B, sorry. So at this point, B is going to go up to 4. Then we're loading 45 into D. Then we're pushing it onto the stack. And as you can see, we're doing this process a whole bunch, where we're loading a value, pushing it on the stack immediately. So once again, this is another block where we can kind of just like power through it. So OX45, 4E, 54, 45, 52, 20, 4B, 45, and 59, 3A, and 20. Let's just double check really quick because we don't want to mess any of these up. They might become important. 45, 4E, 54, 45, 52, 20, 4B, 45, 59, 3A, and 20. And the value in D is now going to be 20. Then we are loading C into B, or loading B into C, my bad, and then loading 1 into A. You can also update our instruction pointer at this time. And then at this point, we're performing a write. And now, this is going to dive a little bit into some of the disassembly that I didn't explicitly cover. If you do disassemble it very thoroughly, you'll find out that the stack is stored in like the upper part of memory, so like at really low addresses. So it's going to be like in the memory at like OX01 and OX02 and stuff like that. And so A here is pointing to a write call. And so we just spent a whole bunch of time loading everything. A here is probably a file descriptor, which we can actually just look at the write call again. And then so B is the pointer to our buffer, which is 4. And C is how many bytes we're going to be writing out, which is 11. And so what we could probably do is directly paste these after removing some new line characters into our UTF-8 to hex converter. And we can see exactly what's getting printed out here. And then we know that our first one is invalid, and we have enter key. How do we know this first one's invalid? Well, because we're starting at 4. So 4, and so 1, 2, 3, and then 4. And so here we have enter key and then a space. And this is good. Why? Because we got that exact message in our program right here. So we know we're on the right track. And so we could make some note maybe that it printed that out. I'm not going to do it. It's not super necessary. But for longer programs, you might want to do something like that. And then so we'll continue to 3-4, where we are popping into C, B, and A, and then pushing them back onto the stack. You'll notice that this is kind of weird. When I ran into this initially, I wasn't exactly sure why this happens, and I'm still not exactly sure. Any insight would probably be appreciated. Just because, like, you're pulling values off the stack, putting them back on in the same order, and then instantly overriding the registers. So, like, these 6 instructions, like, actually just don't do anything. So we're loading 40 into B, B into C, and 0 into A. And then we're performing a read. Now, if we go look at our read syscall, it's probably linked down here, yep. You'll notice that A here is going to be a file descriptor, which is 0, so that means reading from standard input. the second argument, which is B, which is OX40 in this case, is the pointer to our buffer, and C is how many bytes we're reading. So this means that in our memory, from OX40 to OX4B is our input. This is where our input lives. And so this is important. You get 11 bytes of input, and it's going to live on the memory. And for now, we're just going to leave this blank. If you were maybe simulating memory in a more, I guess like an emulator, you might want to initialize this to some character that you would recognize, for example, like an @ symbol or something. Or you could also just set it to a ridiculously high value so you know it's yours. It's like FF or something. Oh, that should be a OX there. So we know that we have control over this block of memory through this read call. Then we're pushing some values onto the stack again. Or sorry, we're popping off the stack. So we pop off to C. So C is going to be 20. Go down there. 3A is going to go into B. Get rid of that. And then A is going to get 59. And then we can delete this off the stack. We'll pop it. So then we are loading FE into D. FE. And then we're loading A4 into C. And then, as you can see, we're performing some more set memories here. So we have 4 more of these to kind of go through. So let's just do those really quick. So we have one at A4, which will go right here. So that's OXE4, and that's going to give us FE. Then we have one at 9E, which is go right here. It's going to be 6-1. We also have one at A3, which is going to be CF. And OXA2, which is going to be just a value 3. So that's those covered. We should also just make sure we're clearing up our C and D registers. So D is going to be holding 3. C is going to be holding A2. Then, as you can see, we are then performing a jump. So remember that I is your instruction pointer. And so it's currently pointing to whatever instruction you're looking at. This means that whenever you modify it, you're going to be jumping. Because if you remember looking at the disassembly, Ghidra is, or in the disassembly in Ghidra, the program is loading based off this offset I. So we can jump all the way down to 6.3, and we know that this value is incremented before it's loaded, because it's initialized to 0 and then incremented. So we're going to go down to 64. This is typical behavior with jumps, as you go right below the line. So OX64 is now our new instruction pointer. And here we're loading some more values. So A is going to be 40, B is going to be 9D, and C is going to be 9, and then D is going to be 2. And then at this point, we are adding D or I to D. Now, you have to be careful when like adding I to things, just because it can hold like a little bit of a weird value. In order to verify this, what we can do is we can actually go look at our output and look for line OX68 in our instruction pointer. So here on OX68, it looks like the result of this is going to be OX6A. So just something to keep in mind. And so let's go ahead and drop that in here. And that's because we're adding this OX68 value to 2, which is going to give us that A. And then we're pushing it onto the stack. Then we jump again to 4D. And these jumps are in there to intentionally confuse you. Like, there was no reason to jump here and then directly back. Now, I don't actually know that. I don't know why I said that, but like it could be in there for a reason. I'll give the benefit of the doubt. So we add C to A, 4-9. And then we add that OX9 to 9D. Now, because I'm not a wizard, we do this like that, and we get A6. And we can also verify that just by looking for that 4E line. So, where is it? We added B. Yes, we did get A6 there. Then we load FF into D. Now, since we're dealing with 1 byte registers here, and we know that because they were offset by one byte from each other, this means you can technically overflow a register, and you will basically end up subtracting 1 when you add FF to it. So you could think of this as 2 ways. You could essentially be observing 2's complement, or you could just add 255 to the value and then subtract 256, because that's how much you're overflowing. So basically just think of FF as -1. And you'll notice that we are adding this -1 value to A and B, so these are both going to go down by 1. So 48 and A5. Then we're pushing them both onto the stack. So push 48, push A5. Then you'll notice that we're loading some memory. And at this point, we are loading OX48, which is our input. So this means that OX48, this value in A, is under our control. Then we're loading from B, which was A5, which is going to be OXBO. So at this point, we compare A and B. Now, I'm going to operate under the assumption here that I want to pass this comparison, because it looks like what's happening is we're comparing our input against some of these values. And so probably, like, you could wager a pretty decent guess here, just based on like problem solving experience, that we're probably going to be doing some input matching at this point. And so we want OX48 to go ahead and be equal to this value of OXBO. So let's go ahead and assume that. At this point then, we can add our flags for our jump here, which I conveniently have closed. So we're going to go ahead and assume that with our jump flags, that if it says N, we're not going to take it, and if it says E, we're going to take it. That is how it works in the back end if I had the actual flag values, because the comparison operator and the flags in the jump, they will compare to be the same thing if it's checking for the right thing. So at this point, we pop B and A back off the stack. So we're going to load A5 back into this and 48 back into A. Get rid of those. And then we're setting D to 61. And at this point, we are jumping to D if that comparison failed. Now, if you remember, we want to avoid hitting this region of OX71 to OXAD. So let's take a look at what happens if we go to 6.1. It looks like we perform some operations, and it looks like we're actually popping I off the stack, which is kind of interesting. And if we look at our stack, it jumps to 6A, which is right here. And then we perform some more comparisons. And so we would fail this jump. And so, yeah, we would hit this region that's bad, because here we would jump to OX70, which is the jump directly to OX71. So we don't want to do that. So let's go back to that comparison. I'm going to sneeze. All right, just kidding. So let's see. So we had just loaded this in to D, and we assume that we are not taking this jump. Why? Because we passed this comparison. We are pretending that we passed this comparison by passing the right value to our input. At this point, we then are loading FF back into D, and then adding it to C, which is now going to go to 8, because we're subtracting 1. Then we're loading 0 into C, or into D, and comparing them. And then, if they're not equal, we're jumping back to OX4F. At this point, they are not equal, so we're going back to 4F, which is right here. So we set D back to FF, and then we subtract 1 from A and D one more time. So 47, A4. And then it turns out we're performing that exact same process over again, where we push them onto the stack, load the dedicated memory values of both of them, and then we compare them. And it turns out we've just decremented. So OX47 And we want that to be equal to this FE value, since that's what's going to come off when we pop off A4, or when we grab A4 from our memory. We assume we pass this comparison. We're going to pop them both off the stacks. These are going to go both come back here. And then, once again, we're going to jump to 6-1 if that comparison failed. We're assuming it did not. So then, we're loading back and we're decrementing C one more time. Then, we set D to 0 again and compare. And if not, we're going back to 4F. And so you'll notice that we're going to keep repeating this process where we decrease A and B to load the next values in the input and whatever this junk is. We compare them, and C is going to continually subtract until it's equal to 0. So at this point, you could evaluate the rest of it, or you could make an assumption and kind of run with it. Personally, I'm kind of a gutsy person. I kind of like just making assumptions and running with them. So at this point, I can assume that we are going to continue comparing these values. And so this means our input wants as many of these values in it as possible. But we have to be careful, because right now we're focused on 4.7, and our C value is 7. This means that we're probably only going down to 4.0 and not past it, which would make sense because we don't have control over anything lower than that. But there's definitely more than 7 values left after that FE. And so this means that we are taking 1, 2, 3, 4, 5, 6, 7, 8, 9 values, and not these last two. So this means our input needs to follow this format. Now, let's say that we inputted this into the program, and let's pretend that we passed all these comparisons. And right here, when we added D to C, let's pretend that we went down to the C value of 0. And then we passed this comparison of C and D. At this point, what would happen is you'll notice that we have a stack instruction, because we're going to load 4F in here. And we're pushing we're pushing C and popping it into D. So essentially we're zeroing out D. Then we're popping off the stack into I, and this is going to take us to 6A. So let's go over to 6A, and then we're going right below it. So we're loading 0 into C, that's already done. We're comparing D and C, that would pass. Then we're going to OXAD based off this equal jump. So let's go down to 8D. We're going 1 past it. And then at this point, you'll notice that we have now entered the win. We have made that jump to 8E. And so this tells me that this is the output, or this is the input that we want to give our program. And even though we have 11 bytes of input, we only actually need these 9. The last 2 are just junk bytes. So let's test our theory. So I'm going to connect another terminal up in. Let's clear this out. And then let us go ahead and go to my home directory. Let's vim our input.py. Let's get rid of all this. Because basically the way I like to do this is like with a name pipe. So basically like an MK5 pipe. And it's really simple to do with Python. So all you do is you create a byte array. So like literally just, let's import our bytes. So B9, 61, C9, 97, 5D, 03, CF, FE, and BO. And then we know that our last 2 bytes are junk bytes, so we're just going to input some, let's just put 1s here, I guess. And then we just write them to standard out using sys.standardout.buffer.write. Close that. And what we can do here is I have made a pipe already just called pipe. It already exists. It's like if I ls, you'll see that pipe right there. And so what I can do is I can say python imp.py and then pipe it into the pipe. Well, I guess like send it. I don't know. This is not like call the pipe, I guess, but that's like the verb I use because I'm an idiot. And then let's call BabyRev and then give it the input from our pipe. So we can run this, and now it's waiting for our pipe to have input for it to consume. We run this, and we get our flag. And so, as you can see, that's exactly what happened. So we're good. Now, the other approach that people have considered taking with this is writing an emulator. I think I mentioned it before. Pretty much, if your goal is to write an emulator for this, you have to pay a little bit more attention to how it works, and you'll have to do a little bit more investigation into the actual source code. Personally, I didn't think like the investment was worth it because I figured that it's only like 200 something lines of code. How bad could it possibly be? And so I chose to do it by hand. However, if this got much longer, I would definitely consider writing an emulator for it, and you'd have to pay a lot of attention to how you implement your mem and your stack. So yeah, I don't know. Hope this helps. If you have any questions, I guess like message me on Discord. And yeah, have a good day.